Welcome back, everybody. Today we're going to be talking about the chain rule, which is a rule in differential calculus that allows you to take the derivative of functions that are essentially combinations of two other functions wherein one is nested inside of the other. So an example of a situation where you would use the chain rule would be something like e to the power of sine of x. You could think of this as a combination of two functions. Let's say like we had g of x was equal to e to the power of x, that's one function, and k of x is equal to sine of x, that's the other function. And you could see that if we were given these two functions and this one, we could see that this was equal to g of k of x. That would be sine of x, e raised to the power of sine of x. And so we're going to deal with this right here. F of x is just some arbitrary function, which is equal to g of k of x, a combination of two functions wherein one is nested in the other, but in abstract terms. And we're just going to work with this expression right here and see if we can find some abstract rule that allows us to generalize and take the derivative of functions wherein we see this situation show up in the future. So if we saw something like natural log of x squared, we'd be equipped to deal with that. So let's get into it. And so in order to figure this out, let's just start with our formal definition of our limit, which is going to tell us that f prime of x is going to equal the limit as h approaches 0 of f of x plus h, which in this case is going to be g of k of x plus h minus g of k of x. All this is going to be divided by h. And it might not be immediately obvious how we should proceed from this point. It can be pretty intimidating when you see these arbitrary functions, g of k, they're not specific, they're very abstract, and it's like, how can I get this k of x plus h out of here? How can I even get this into terms that I can work with when I don't even know what these functions are? And that's a very reasonable fear, but it's actually not necessary in order to take the derivative of this function, and the answer is to look at what's inside of our parent function here, g of x. And in order to give us a little bit of a clue, I want you to consider what happens if I was to take, for example, the derivative of f prime, or the derivative of f of k of x. Well, if we were to just plug in values using our formal definition of a limit, this would equal the limit as h approaches 0 of f of k of x plus h. That's just f of x plus h, but in this case we're plugging this in for x. And then we're going to subtract f of k of x. And then what's going to be in our denominator here? Well, we're just going to get k of x plus h, k of x plus h, minus k of x. And that's just plugging in x plus h here and using our x here. That's really all it is. And so if we plug in this abstract function here for our x, this is what we would get. And so this is equal to this. And so if I can find a way to get this, which is basically what we have in the numerator here, except with g's instead of f's, this is basically what we have. We have g of k of x plus h minus g of k of x. That's exactly the same thing we have in the numerator here. So if I can find some way to get this into the denominator here, I can get this into terms that I can work with, because that's going to be equal to f prime of k of x, or in this case, g prime of k of x. And so in order to do that, what I'm going to do is multiply by k of x plus h minus k of x, all of that over k of x plus h minus k of x, because that's essentially the same thing as multiplying by 1. So I'm going to do that now. K of x plus h minus k of x. And from this point, I can keep my limit out front. I'm going to put brackets around this. And here I can just swap these denominators, the reason being that multiplication is commutative, so it really doesn't matter which term comes first. That is to say that g of k of x plus h minus g of k of x, all of this over k of x plus h minus k of x, multiplied by k of x plus h minus k of x over h. These two expressions are going to be equivalent. And we saw in my video on limit properties, I went ahead and proved this, but the limit of two products is going to be equal to the product of those limits. And so I can basically distribute this limit. I can say that this is equal to the limit as h approaches 0, g k of x plus h minus g k of x. All of this over k of x plus h minus k of x, multiplied by the limit as h approaches 0 of k of x plus h minus k of x, all of that over h. And now here, this first term here, we've just defined that this is equal to g prime of k of x. This is exactly what you get when you plug in g prime of k of x, when you plug in this into the formal definition of the limit. And so this is what we get here. And then we're multiplying by, well, this is just the formal definition of the limit, or formal definition of the derivative for k of x. And so this is just equal to k prime of x. And so if f of x is equal to g of k of x, g of k of x, then f prime of x is going to equal this. And this is going to be our chain rule. F prime of x is going to equal g prime of k of x multiplied by k prime of x. And so let's look at an example of this with something that we already know how to differentiate. Because basically the only thing that we could differentiate right now at this point in our calculus journey is going to be polynomial functions. So let's take this, which is x cubed minus 2x squared. And let's see if we can evaluate this two ways. The first way is going to be without our chain rule. We'll just take x cubed minus 2x and square it, and we'll evaluate it this way. So this is going to be equal to x to the power of 6 minus, it looks like 4x to the fourth plus 4x squared. And so we can take the derivative of this using our power rules. This is the derivative here is just going to be equal. I'm just going to do it like this. I know it's not conventional, but I'm lazy. This is going to be 6x to the fifth minus 16x to the third plus 8x. So that's going to be our derivative. Now let's try the chain rule that we just discovered. F prime of x is going to equal g prime of h of x multiplied by h prime of x. And let's see if we can apply that here. Well, first we need to, when you're dealing with problems like this, first we need to determine what we're going to say as our g of x and what we're going to see as our h of x. So here I see the smaller function inside here, x cubed minus 2x, is the one being squared. So I'm going to say that h of x is our smaller function here. H of x is going to equal x cubed minus 2x. And I'm going to say that g of x is equal to the outermost function, which is x squared, right? You can see that that's what's going on here. G of h of x would be x cubed minus 2x squared. And that's what we have here. So let's try to take the derivative using this. The first thing that we have to do is take g prime, which is just 2x, but applied to h of x. So this is going to equal 2 times x cubed minus 2x. And then we have to multiply by h prime of x. Well, h prime of x is just the derivative of this expression here. And so that's going to be multiplied by 3x squared minus 2. Okay? And so now we can multiply all of this out. This is going to equal 2 times, what would we get here? We would get 3x to the fifth, and then we would get minus 2x cubed, and then we would get minus 6, looks like 6x to the fourth, and then we would get plus 4x. Oh, this would be, that's a mistake. This is not going to be 6x to the fourth. This is going to be 6x to the third. Yeah. And so then these are going to add together, and we're going to get 2 times 3x to the fifth minus 8x to the fifth, or x to the third, sorry, plus 4x. And then when you multiply out the constant, we get 6x to the fifth minus 16x cubed plus 8x. And as you can see, these two expressions are equivalent. So our chain rule does indeed work.